we'll be exploring the forward algorithm together. So let me introduce myself first. So I'm Elston. My name's Elston. I am from Singapore, and I am an AI enthusiast, a lifelong learner, and a programmer. And those three A's are also actually the name of the course I'm studying right now, which in Singapore Polytechnic, which is Applied AI and Analytics. I'm currently an intern for A-Star, Agency for Science, Technology, and Research as well. So with that quick introduction out of the way, let's see how to train a feed-forward neural network. So traditionally with feed-forward neural networks, so we define X as the input, so there's only two inputs basically, two input nodes. And then we define W1 to be the weights between the input layer and the hidden layer. And we matrix multiply the W1 with X. And then we add the bias. There's two biases, B1 and B2. So we add the biases, and this gives us A1. And what A1 is the weighted sum of inputs. However, the weighted sum of inputs currently is linear, and we don't want it to be linear because it's bad. We want to add non-linearity to it, and we do this by applying an activation function, any activation function, like ReLU, leaky ReLU, 10H, whatever. So we do this so that the model can learn more complex patterns. So then we get H1, and then we repeat this whole process from the hidden layer to the output layer, but with H1 being the input now for the hidden layer to the output layer. After we do all of this, we get one value. We call that y hat, which is the predicted value of the model. And we use the cost function to see how well the model predicted, well, how well the y hat fed against the actual value. So how well was the model's prediction? And then we compute the gradients of the cost function with respect to all parameters using backpropagation, and then use stochastic gradient descent to minimize the cost function by adjusting the weights and biases. And below is just an example of how we get the gradients, the gradient of the cost function with respect to weight 1. And this whole thing is just a small example, but this procedure of doing stochastic gradient descent over a large number of parameter and data has proved effective for deep learning over the years. And I'm sure most of you, like maybe even all of you, use backpropagation now for any work that you do, or any models that you train. But does the brain actually do backpropagation? So I think most people have a misunderstanding with this question. I think most people think that the brain does backpropagation because neural networks are supposed to be modeled like the brain. So and I even asked my teacher actually, and my teacher, one of my teachers, my form teacher, said that he thought that the brain did backpropagation. So you know, even teachers have this misunderstanding. But anyways, according to Lillicrap et al. In Backpropagation and the Brain, feedback connections send error signals for backprop to adjust synapses, whereas in the brain, feedback connections are used for different purposes, and the brain is thought to learn in mostly an unsupervised fashion, whereas backprop has classically been described in the supervised learning setting. So even though backprop trained models has been shown to be able to account for observed neural responses from past works, backprop-like learning cannot be implemented in the cortex, unfortunately, since there are loads of major difficulties despite people trying to prove that backprop works in the brain. So what are some of the problems of backprop? being in the brain. So the three problems that Geoffrey Hinton stated in his paper is that number one, there is no convincing evidence that the cortex explicitly propagates error derivatives or stores neural activities for use in a subsequent backward pass. Number two, if backpropagation was used in our visual system, there would be bottom-up connections from one cortical area to an area earlier in the visual pathway. But this does not mirror the top-down connections we have in our brain. Number three, last but not least, to deal with streams of sensory input without taking frequent timeouts, the brain has to pipeline sensory data through different stages of sensory processing, and it needs a learning procedure that can learn on the fly. The perceptual system needs to perform inference and learning in real time without stopping to perform backpropagation. Also, there's out of all the major difficulties, there's actually a lot of major difficulties, but one of them caught my eye. It was extra interesting to me, and that is this. So in Backpropagation and the Brain, again by Lillicrap et al., they stated that feedback in brain alters neural activity, and that's one of the major difficulties for why backprop can't be used in the brain. So it basically says that in backpropagation, after computing the gradients of cost function with respect to parameters, we use stochastic gradient descent to only adjust the weights and biases. We only adjust the weights and biases. We don't touch anything else. We do not change the activity states of neurons computed by forward propagation. However, in our brain, the role of feedback connections are different. So for example, in the cortex, the connections influence neural activities produced by forward propagation and serve a number of functional roles. For example, top-down control through feedback connections has a well-established link with gain control, which is the enhancement or suppression of neural responses, depending on, for example, attention to a particular feature in the visual field. Feedback connections in the cortex can even drive activity rather than just modulate or enable it. So in backpropagation, we adjust the weights and biases, and we don't touch the activity state of the neurons computed by the forward propagation. However, in the brain, the feedback connections actually change the or influence the neural activities produced by forward propagation. So that's why backpropagation cannot be implemented in the brain, because if you change the weights and biases, then you're also actually changing the activity states of the neurons. So that's where Geoffrey Hinton comes in. So he's the same guy that publicly stated that we should throw away backpropagation and start everything again from scratch, despite being one of the researchers that had proposed backpropagation in 1996. During Neural Information Processing Systems 2022, he proposed the forward-forward algorithm, which is a new learning procedure for neural networks. It's inspired by noise contrastive estimation and his very own Boltzmann machines. So what is the forward-forward algorithm? So this new algorithm, this new learning procedure that Hinton has proposed is more accurate in terms of how the brain works, unlike backpropagation, and allows for pipelining of input through processes by dividing the process of getting the gradients into two separate phases, the online phase, which is meant to correspond to wake, and the offline phase, which is meant to correspond to sleep. So what you're seeing here is, on the left, feed forward with backpropagation were very comfortable with one forward pass and then a backward pass computing the gradients. However, in the forward algorithm, we do not have any backward passes. We only have two forward passes, one being the online phase and the other being the offline phase. Another thing about forward is that with feed forward with backpropagation, the cost function comes at the end of the forward propagation. And the objective of it is to see how well the model, the predicted value of the model fed against the actual value. So there's only one, and it comes at the end. Whereas for forward, it does not come at the end. It has multiple cost functions at each layer. So each layer basically has its own objective function. So this is the algorithm for the cost function, and it looks a bit weird right now, but basically every layer has a goodness function, or goodness value, sorry. So every layer has this thing called a goodness value, and the way you get the goodness value is from a goodness function. And the goodness function that Hinton had stated in his paper is this. So this basically, we're taking the sum of the squares of the activities of the rectified linear neurons in the layer. So that's what we're doing to get the goodness value for each layer. And basically what the cost function is doing is that for the online phase, so for one of the forward passes, where you're feeding it positive data, it aims to make the length or it aims to make the goodness value higher, or high enough for the model to detect positive data. And for the offline phase, which is the other forward propagation or forward pass, you feed in negative data, and the cost function is trying to make the goodness value for each layer as low as possible, or low enough for the model to be able to detect negative data. So offline phase and online phase, real data is being fed into the model from real data is so for the online phase, basically we feed in, as I've said just now, real data, or rather positive data. I think those two terms are interchangeable. So we feed, let's just call it positive data. So we feed positive data into the model from a data set, or from any external sources, and for each layer at each time step, the model tries to make the goodness value for each layer as high as possible, or high enough so that the model can predict the positive data. And negative data rather than fake data, I mean, they're still interchangeable, but let's call them negative data instead. Negative data is fed into the model during the offline phase. So it can be either from modifying real data, or you can generate negative data from a generative model, and the value of the goodness in every single layer will be minimized as much as possible, so that the model can detect or predict negative data. So the way that the model predicts if a data is positive or not is that it gets the goodness value, and the goodness value is basically that summation equation, and after you get the goodness value, you subtract a threshold, which is the threshold would be a hyperparameter. You subtract the threshold from the goodness value, and then you feed the result of that to a logistic function, which outputs the probability of the data being positive data. But I think most of you might be wondering right now, what is real or positive data? So real data is what you want to model, right? So let's say we are training the model on one of the most common data sets, the MNIST dataset. And the MNIST dataset is just a data set full of images of handwritten digits from 0 to 9. And real data would be, for example, an image from an image from the MNIST dataset, but with the label of the corresponding image part of the image itself. So this is a 4, right? And the label of this image gets 1 hot encoded in the first 10 pixels of the image. And what is thick or negative data? So if with positive data you want to have as high goodness value as possible in each layer, for negative data you want to have low goodness value for each layer, low enough so that the model can predict that it is negative data. And this is the example for a negative data. So it's the same image from the previous slide. However, you can see that the 1 hot encoding is wrongly 1 hot encoded, I guess. It's the wrong label, basically. And this is just a function for, we'll get back to this later. Anyways, one more thing actually about the forward algorithm. During the forward propagation in the forward algorithm, we do not just matrix multiply the weights with the input. So in well, okay, I have to scroll. Okay, over here, right, we just matrix multiply the weights with the input, and that's, yeah, we just matrix multiply the weights and the inputs. However, in the forward algorithm, during the forward propagation, we do not just matrix multiply the weights with the input like that. We have to normalize the input first, then we matrix multiply the weights with the normalized input. And to learn a single hidden layer, I mean, basically why we do this is that to learn a single hidden layer, for the model to learn a single hidden layer, we just have to make the sum squared activities of the hidden units, or basically the goodness value high for positive data and low for negative data. So if we do not normalize the input, we basically are just passing if we do not normalize the input, basically we are using the activities of the current layer to the next layer. So we're basically passing the information of the activities of the current layer to the next layer. And if we do that, the next layer can just use the length, or rather the activities of the current vector or the previous vector, the previous layer, to determine if it is positive or negative data. So the next layer doesn't learn any new features. So yeah, we just normalize it so that it loses its length, but it still keeps its direction. So I did mention the MNIST dataset just now, and I'm going to be, well, in the model, in the research paper, in the research paper, Geoffrey Hinton actually compared the forward with a few other models on the MNIST dataset. So that's what we're also going to do. So this is just a quick model that I got from the internet, basically from Keras TensorFlow, and they basically have a flattened layer and then a dense layer of 128 neurons to a output layer of 10 neurons. And basically we get this validation loss over training, and the validation accuracy is 97.5% in 21.1 seconds. So in 21.1 seconds we get a validation accuracy of 97.5%. Let's see how the forward algorithm does. So we first put labels with images, right? to get the positive data. So we have X and Y, X being the images and then Y being the labels, obviously. So we just put the labels onto the images, which is normal. That's how we get positive data. But for creating negative data, we actually have to get random permutation of the size of the X, basically our training model. So what we do here is we basically just shuffle the labels, and we assign random labels to random image, not random images. We assign each image to a random label that's not theirs, basically. So that's how we create our negative data. And this is how we train the model. So we do a forward pass first, normalizing the input, and then matrix multiplying, all that good stuff. And then we get the goodness value of the layer. So we do that just like this. Then after that, we calculate the loss. So this loss, what this does is basically it increases the goodness value of every layer. So okay, during the online phase, when we're feeding positive data into the model, this loss function makes the goodness value of every layer as high as possible, or high above the threshold, high enough for the model to predict that it's positive data. And during the offline phase, when we're feeding just negative data into the model makes the goodness value of every single layer in that model as low as possible, below the threshold, so that the low enough so that the model can predict negative data. And this is how we calculate the derivatives. So we calculate the loss and then the derivative of the layer. And the way that we predict images, the way that the forward algorithm predict images is that, so we have for MNIST dataset, we have images of digits, hand-drawn digits from 0 to 9. So for each label 0 to 9, so okay, for example, if we pass an image in that we want to predict, we go through every single possible label, so 0, 1, 2, 3, all the way to 9. We put every single label possible on the image. So we put we one-hot encode the image, the first 10 pixels of the image with 0, and then 1, 2, 3, all the way to 9. And for each label, we get the total goodness value of that image with the label. And after that, we just get the maximum, the label with the most goodness value. And that will be our prediction, basically. So that's how we predict images. So with almost the same duration of training, it achieves an accuracy of 90.7% accuracy, which is not that bad. And I actually tested the forward algorithm on another dataset or another problem. So I got this blood cell dataset from Kaggle, and basically it contains images of 4 different types of blood cells. I'm so sorry if I butcher the names. Eosinophil, lymphocyte, monocyte, and okay, I did not change the name of the last one, but the name of the last one should be neutrophil. Yes, neutrophil. So the model that I used to train the model that I used with backpropagation is this model. So this is just a convolutional neural network, basically, and then with dropout layers and fully connected layers, 4096 inputs in the input layer, 4096 neurons to 512 to 128, and then the output layer will be 4 neurons basically, because 4 labels. So yeah, and then we get a loss of 0.0540 at 1296.5 seconds. So that's the performance of backpropagation on this problem. For the forward algorithm, however, so it was a bit weird. So I actually used a bunch of different combinations. So I actually resized the image. So I resized the image to 64 by 64, and it has 3 channels. So we get 12,288 neurons for the input layer, and then for the subsequent layers, I used a bunch of different combination, but I think the combination that I found works the best currently, because it's not fine-tuned enough. I think this can get better performance. Honestly, I think this can get better performance, but currently the best combination I found so far is 300, 200, 300, and this gave me so the train error is significantly lesser with 353 seconds and 392 seconds. These two are just the two of the best performances I've gotten. So the training time is significantly lesser. So the first one with 2.5k epochs got a train error of 0.3125 and test error of 0.53125. Then the second one, I used 2.9k epochs and it got a train error of 0.2656 and a test error of 0.578. So I don't know, maybe the second one might have overfitted, but who knows. But yeah, those are so okay. So this is the, bear in mind, the previous one we actually used dropout layers, and it's using convolution layers, max pooling, all this stuff. So it's extracting the features. However, for this one, it's just forward algorithm, no dropout layers, no convolutional layers, anything like that, just plain forward algorithm, just forward passes. So this, I think it's quite good, honestly. If you want to help me improve, maybe you have some ideas or you want to explore the code, I've actually put up the code here. You can find my GitHub, ELSTUHN Elston, and then the repository is ffbcc. So I've just copied and pasted the code there. So if you want to help me like improve the if you have any ideas, and the code is just all there, you can just fork it, and then if you want to improve, go ahead, whatever. So what are the disadvantages and advantages of the forward as compared to the back propagation? So the advantages is that the forward algorithm can be used when precise details of forward computation is unknown. So in back propagation, you can't do this. If you don't have any details on the forward computation, you can't do back propagation. But forward solves this. Forward can also pipeline sequential data while learning. Again, backprop can't do this. It also cannot it does not need to store neural activities or stop to propagate error derivatives. This is one of the problems that we've stated why backprop can't be used in the human brain. So what are the disadvantages? It has less generalization power. So it generalizes worse than backpropagation by a bit, I guess. And it's somewhat slower than backpropagation. And it is unlikely to So forward is unlikely to replace backpropagations for situations where power is not an issue. However, some of the use cases first, all right. So Geoffrey Hinton, this is just two of the use cases that Geoffrey Hinton stated in his paper. I'm sure there's loads more use cases, but these are just two that he stated in his research paper. So it one of the use cases is it can be used as a model of learning in the cortex, and the second one is that it can be used as a way of making use of very low power analog hardware without resulting to reinforcement learning. So again, we said that unlikely to replace backprop for situations where power is not an issue. So yeah, I think this this forward algorithm, this new learning procedure has a lot of potential. Like I think there's the previous two problems, that this blood cell dataset and the MNIST dataset, so actually for the MNIST dataset, right, Geoffrey Hinton has achieved better results on his paper. So I think the thing is he hasn't published his implementation. So I think the current implementations can be improved to perhaps achieve the results that he got for his paper. And I think there's a lot of potential in the forward algorithm. There's a lot of questions. There's a lot of different things we can explore in the forward algorithm. And it's a very interesting learning procedure, definitely. I would like to thank all of you for listening to my talk on the forward algorithm. This is actually my first time doing a talk, so I'm a bit nervous throughout this whole thing. I don't know if you can tell, but yeah, thank you so much for sitting through this, my first ever talk. I would also like to publicly thank my two bestest friends in the world, Steele Farnsworth and Andre. They've helped me through a lot, so thank you very much. Love you guys. Yeah, that's basically all. Thank you so much.
So just to kind of summarize this, right? Forward is closer to how the cortex works or the brain works, right?
Yeah.
And there are a lot of situations where backpropagation, well, maybe not a lot, that can't be used. I mean, is it correct that if you use forward, then you can kind of have a model that's learning live as you use it?
Yeah. So that means if you use forward, because with backpropagation, the feed forward with backpropagation is its official name. If we use that, we have to go back in time to change the weights and biases. But with forward, you don't need to go back at all. So in a sense, sort of learning live, yeah, you can pipeline data, so you don't have to go back. Yeah.
That's fascinating. I think that could possibly be a game changer, at least in the current AI space, maybe. But we'll see. I'm looking at this as a going back to basics kind of move by Geoffrey Hinton, right? One of the authors of backpropagation itself. What I mean by that is going back to basics in the sense that we're going back to the original inspiration of neural networks, which is essentially the brain, right? The human brain. So I think this is fascinating. We have a couple of questions from the audience. I'm going to go through. We have 3 right now. Feel free to keep asking more questions, guys. I'm going to paste this in our Zoom chat, and I'm going to read it as well. But just in case you can't understand. Oh, I think it was already pasted as well. So the first one is from Sunny. For forward, the rewards function is evaluated per layer. Wouldn't it be more expensive as the reward is ran at n number of layers? If yes, would it be worth the extra overhead?
So I think okay, I don't think it would be more expensive as the reward is ran at n number of layers. Like the cost function is, or the objective function is ran at n number of layers. However, with feed forward with backprop, you have to, although there's only one cost function or one objective function, you have to go back in time as well. So you have to go through n number of layers twice, basically. But I don't think the computation for the cost function would take a lot of time or computations anyways. So I don't think it's a huge problem. I don't think it will be more expensive. If anything, it's more convenient, I guess. Yeah. So I don't think it will be more expensive. Yeah.
Okay. Let's go with Carl's question next. So does each loss function represent a different form of loss? So is it like a multi-loss function problem, but you deal with it little by little per layer? He has a follow-up to this. Or if it's like a multi-loss function problem, is it like you are dealing as separate loss problems per layer?
It's not separate. It's not a multi-loss function problem. No, each loss function does not represent a different form of loss. So it's not a multi-loss function problem. It's the same loss. Yeah, it's the same. Yeah, we use the same algorithm for every we use the same algorithm to calculate loss for every single layer. So it's not a multi-loss function. Yeah.
Okay. Sounds good. The last one from the audience so far is from Xavier, and it's a philosophical question. So, will deep learning improve our understanding of the brain, or will our increasing understanding of the brain lead to the creation of better computers?
I think, we don't know like 100% about the brain now, right? So, I think it's a bit impossible to create a model that would like 100% impersonate the brain. So, we can't really improve our understanding of the brain through deep learning just yet. It's more of like we're exploring more of the brain to increase how much neural networks are modeled according to the brain. So yeah.
Okay, that makes sense. We have a new one from Nins. So how will FF improve new things such as transformers?
I don't think FF will. Okay, so FF will not replace backpropagation. It's very unlikely to replace backpropagation. So everyone will still continue to use backpropagation as of right now, because forward is not really reliable as of right now. It's only used for very specific cases. So it will not improve new stuff such as transformers. I don't think it will improve, or at least in the current state, I don't think it will improve new stuff such as transformers or whatever. Yeah.
Okay. All right. Feel free to ask more questions, guys. For now, I'm gonna ask one of my own. So can you tell us about some of your current active projects? Because you mentioned that you have a couple going on right now.
Oh, current active projects. So it's just relating to the forward algorithm. Sure. I am still researching on the forward algorithm, because in the paper that Geoffrey Hinton published, he asked a bunch of questions at the end, a bunch of research questions that we can answer through playing around with the forward algorithm. So I am researching that right now. One of them being using convolutional layers along with the forward algorithm. That's one. And then how it scales with more complex problems. Yeah, but other than that, current projects includes like making neural networks from scratch. So I'm working on. Currently, I put everything on pause, to be honest, because of exams. But I'll be continuing them like from today because it's my holiday. So some of
Yeah.
them is just building neural networks from scratch. All this. Uh, I am thinking of making a game as well. Yeah.
Okay. A game related, any other qualifier aside from just, a game, or
And any what? Sorry.
I mean, what kind of game are you thinking about making, or
Um.
you don't know yet?
Okay. I don't know if I should say this because
Oh, it's
it
it's okay
sounds
if you don't want to
super
talk about it
super
yet.
it sounds super dumb, but so I play this game called Roblox, right?
Oh no, sure, yeah.
Uh, and they have really weird games like rat washing simulator and stuff. And so that sort of and it was actually quite fun. Those games are quite addicting, no
Mm.
matter how stupid they sound. So it sort of inspired me to make one of my own through learning React JS. Yeah.
That
So that's
sounds
one
good.
idea.
I don't know. I don't think you need to feel ashamed about that. I think a lot of software engineers out there, or anybody taking up STEM courses, are massively inspired by games. I don't think it's something you need to feel ashamed about. So I
Yeah.
think it's something we need to celebrate, right? And tomorrow, I think Sonny will be talking about who's in our audience, right? He's going to be talking about making a real-time game from using Django and stuff. So I think it's great. I think it's great. I think we should celebrate these things. So
Yeah.
another question for me. And I don't know, I'll just throw this out there and see what I can pick off your brain. So, what's a bold prediction that you have in the next few years that you think AI will significantly change in the way we live?
In the way we live. Um, a bold prediction.
Yeah, I
Okay.
mean, so it doesn't have to be, what I mean by bold prediction is
Yeah.
like you feel strongly about it, but you're not really, you don't have a lot of evidence for it, right? You just feel like this is what's gonna happen.
Mm, I think if we're going with bold, I think honestly with AI, like honestly, I think many people will become lazier, honestly, because especially with ChatGPT, I've had a lot of friends uh I think people will be a bit more reliant, like
Mhm.
because a lot of my friends use ChatGPT for their projects as well. So that's not thinking for yourself. And I do know that some person did invent something or make something for teachers and stuff to see if students have used ChatGPT.
ChatGPT.
Yeah, and but it's not implemented everywhere yet. So
Mm.
I think people will continue using ChatGPT and
Mhm.
relying on it for
Yeah.
like homework and stuff.
I
So
am
I think,
100% sure that people will
yeah,
keep using it.
yeah. So yeah, people will be more reliant on it, and then like their English skills won't develop. Yeah, that's
Yeah, I
just
mean, I think that makes a lot of sense, but also I think the creator of or at least the CEO of OpenAI was also saying that it's kind of just like the calculator, right?
yeah.
Maybe it will just help us do things. Honestly, I don't even, my brain isn't as tuned as it used to be, like doing mental maths now, but I think I can still make like decisions based off of those calculations. So I'm not as pessimistic about cat GPT-3 or chat GPT. I think it will unlock new possibilities. I think it will let us do other things that we don't need to, think about how to write it in English or whatever. But who knows, honestly.
That's true. I think with a lot of stuff there's I mean with everything there's always advantages and disadvantages. And this
For
is
sure.
one of them. Yeah.
Yeah, we will see. I think there's a lot of risk. People feel threatened about maybe losing their jobs or whatever, right? But I think that's true for any new technological advancement anyway. It's not as maybe this one is going to be a big wave, so we'll see. We have another question from Carl, I guess, but it's somewhat a bit off topic, as he says. Do you have any other research fields or problems you're interested in, aside from finding more theoretical implications of the FF algorithm?
Any other research fields or problems I'm interested in? Honestly, there's a lot of stuff that I'm interested in, but I'm deciding to focus on one thing at a time because I think it's better that way. But if you're asking about any other research fields or problems I'm interested in tackling, I am interested in neuroscience. That's my newest interest, neuroscience. I don't know where I picked that up from, but just found it interesting. And yeah, honestly, competitive programming as well. I think that's a big thing because I'm still young. I'm 17 years old, and I'm honestly super scared for like hack interview questions. So yeah, I think that's another problem or field that I'm interested in tackling. Yeah, math is a huge thing as well. Currently, I'm learning from scratch linear algebra from MIT. Yeah, that's another thing. But those three are my current like main ones, I guess. Yeah.
Okay. We have a couple of new questions coming in. One from Xavier. What is your dream ML project?
Dream ML project. Dream ML project as in like AI project, like project that uses AI.
Yeah, probably.
So okay, yeah, I'm assuming you mean that I think my dream project that uses AI, honestly speaking, like dude, like okay, a lot of my answers sound super okay, maybe it's because I'm young. I don't know. Maybe it's because I'm young, but it sounds very weird and dumb. But my dream AI project is to possibly make an army of AI robots. Like make an army that could go to war. I think that's because I think that's a very interesting. There's a lot to find out from that kind of project. There's a lot to learn from there. Yeah.
Okay. One more from Stephen. Does forward algorithms suffer from vanishing gradients or a similar issue, or values becoming increasingly smaller after passing through succeeding layers?
I don't think it suffers from vanishing gradients. Because I think that's one of the problems that Geoffrey Hinton stated with backpropagation. There was one section, I can't remember, but I think there was one section talking about how vanishing gradients make backpropagation impossible in the brain. But I do not think forward algorithm suffers from vanishing gradients or like values becoming increasingly smaller or whatever passing through each layer. Because I haven't seen it after researching with it for so long. I think it's because during forward propagation for the forward, we normalize each layer. So we sort of throw away like the length of the layer vector, and we only keep the orientation or direction of the layer vector and then pass it to the next layer. So I don't think there's going to be vanishing gradients or any problems like that. Yeah.